In this video, we shall see what is the shared pages, structure of page table and segmentation. Shared table, shared pages, it is nothing but it is an advantage. It is an advantage of your paging concept. It is an advantage of paging concept wherein you can share the common code. You can share the common code among the environment, time sharing environment. So, here if you see here, one copy of read-only code can be shared among processes. That is, it can be text editors, compilers or Windows system. Shared code must appear in the same location. You should keep in mind that the shared code should be appear in the same location in the logical address space of all processes. Next, private code and data, that is whichever is private for that particular process or editor, those data can be copied separately. It can be copied separately. Here in this diagram, if you see, ED1, 2 and 3 are common in all the processes because we have three processes, process P1, process P2 and process P3. And in all these processes, we have common data, that is ED1, ED2, ED3, and all these are mapped into same place, that is it is commonly shared. 3, 4, 6. Here also if you see, it is 3, 4, 6, 3, 4, 6. Private data is data 1, data 2 and data 3, which are stored in separate frame numbers. Next we shall see what is the structure of page table. Under structure of page table, we have three categories to study. First one is hierarchical paging, second is hashed page table, and third one is inverted page tables. So first one is hierarchical paging. Hierarchical paging is nothing but, as you know the definition or meaning of hierarchy, different levels, that is break up the logical address space into multiple pages. It is a simple technique with two-level page table. What is this two-level page table? As you are aware, till now we have seen only, you have your logical memory and you have your physical memory. Here you will be getting your address generated. Based on this address, you are going to fetch the physical memory. That is your two things, that is your page number and your offset value. With the help of your page table, you are going to fetch the page frame number, and then with the help of your frame number and offset value, you are going to fetch the data inside your physical memory. Here this logical memory is divided into two stages. One is your outer page table, another one is your page table. So that is, page table is nothing but it will have pages inside it. Page of page table. So it is an example or a schematic view of two-level page table scheme. So how this address translation can be done? Till now we have seen address translation L equal to P comma D, that is page number comma displacement. Here what happens, you will be having P1 comma P2 comma D. That is, P1 is nothing but it is an index into the outer page table, that is your first table. Whenever the logical address is generated from CPU, you have P1. Till now we have seen, I repeat, till now we have seen L equal to P comma D, that is your page number comma displacement. Now whenever the address is generated, we have P1, P2 and displacement. So P1 is nothing but page number or your frame number which has the page number to the next page table, that is an index into the outer page table, and P2 is nothing but displacement within the page of the outer table, P2. Next you have exact displacement value. Here if you see, 10 is nothing but your outer page value. Next it acts as a displacement for the inner page value, that is inner page table, that is within a page table. Next, similarly, we have three-level paging scheme. That is your page 1 to offset value. that is 1, 2, 3 and your offset value. That is second outer page, next outer page, inner page and then your offset value, that is displacement. Next we shall see what is hash table or hash paging table. It tells that whenever the address is generated, the virtual page number is hashed into the page table and it contains a chain of elements hashing to the same location. And whenever the page number is generated, it is compared in the chain searching for a match. If the match is found, then the corresponding physical frame is extracted. That is, whenever the logical address space is generated, that is P, it is being hashed using your hash function table, and if it is found, it will give the value, that is R. If it is found, then you can access the physical memory. Next, inverted page table, the last structure of your page table. In this, there is one entry for each real page of memory, and each entry consists of virtual address of the page stored in that real memory location with information about the process that owns that page. That is, whenever we have already studied what is a process, a program in execution, and for each and every process we have a process ID generated. So whenever the address is generated with the help of your inverted page table concept, you have three things to do. One is your PID, that is process identifier. Next you have page number. Next you have displacement. Using this, it will search the process ID, that is I. Using this identifier, it will send the identifier here, copy the displacement and then access the process present inside the main memory or physical memory. This is the architecture of your inverted page table concept. Now the last topic of this chapter is segmentation. What is segmentation? Segmentation is nothing but it is a non-contiguous memory storage allocation. Here we are going to divide the logical memory. Logical memory is divided into variable size, whereas in paging, if you remember, we are going to divide the logical memory memory into fixed size, whereas here we are going to divide it using variable size, and every segment has a segment number. This is most important to remember. Every segment has a segment number and a length which is loaded into physical memory. And memory management scheme that supports user view of memory. What is it? We'll see. Next, a program is nothing but collection of segments, and each segment can have its own logical unit. It can have a main program, procedure, function, method, object, local variables, common block, stack, symbol table and arrays. All these are nothing but the logical units of a segment. So this is the user view of a program. It can have subroutine, stack, symbol table, main program, square root function. Now with respect to this, what we can do is, all these things are called as each segment. How is it? We'll see. Next, segmentation architecture. That is a simple hardware architecture. How we have studied for paging, even for segmentation also we have an architecture, hardware architecture to study. As you can remember, paging, whenever address is generated, we have two things, page number comma displacement value. But in your segmentation, you have two things, L equal to segment number comma offset, that is your displacement value. And segment table always maps two-dimensional physical address. Each table has base value and limit value. This base contains the starting physical address where the segments reside in memory, and limit, it specifies the length of that particular segment. What is this? We'll see here. As you can see here, CPU generates logical address. It has segment number. Instead of P page number, it has segment number. And this segment number is always stored inside your segment table. In your paging, you have page table. In your segmentation, you have segment table. But here in your segment table, you have two things to remember. One is limit and base. whenever the segment number is searched, you are going to fetch the limit value. You are going to check this limit value with your displacement value. If the displacement is less than the limit, then you are going to add the value with your base register and fetch it inside your main memory. Fetch inside your main memory. That is what is being explained here. And always remember that the value of offset, that is D, must be between 0 and segment limit. 0 and segment limit. Next example, as we have seen, each of this program, that is sub functions, that is your subroutine, stack, symbol table, main memory, main program, square root, all are called as each segment. Segment 0, 1, 2, 3, 4. So, for each of these segments stored inside your physical memory, we can write the segment table. Segment table. As you are aware, the difference between your limit and base register, you can see here segment 0. If I see segment 0 is for subroutine function. So here I can see the limit value is 1000. So the starting address is base address is 1400 and limit value is 1000. So totally your value will be 2400. Next, similarly, if I take segment 1. Segment 1, if I search here, I have it placed here. So base value is 6300 and limit is 400. So 6300 first plus 400 gives me 6700. Similarly with segment number 2, 3 and 4. 2, 3 and 4. This is a simple example of your segmentation concept. Thanks for your patience listening.